Now, our second part of our three-part show tonight. We're going to hand over our screen to the students at the U of M's Minnesota Institute for Astrophysics for their popular Universe at Home virtual series. Darcy Ballantyne, who is a Planetarium education assistant here at the Bell, and an astrophysics student and a major in plant science here at the University of Minnesota. And we have Ann Isaacs, who is a graduate student here, and Alexander Criswell, a second-year graduate student in astrophysics, and the graduate coordinator for Universe at Home. I can't wait for you to share all about this great program. So thank you all for joining us. I want to remind the audience there's still the opportunity for you to send in Q&A for this session. So take it away.
All right. Hello, everyone. We are very happy to be here. You'll have to forgive us as we hold on for just a little bit. As was mentioned, we are from Universe at Home, which is a virtual series that the University of Minnesota's Minnesota Institute for Astrophysics puts on. And so this talk is also being live streamed to the Universe at Home YouTube channel, and we're just waiting for that connection to come through. And I see that we have it. So as soon as I get my Zoom window out of the way here, we can go live. So I'm going to hand it off to Darcy Ballantyne and Ann Isaacs. And we are live in 3, 2, 1. We're live. All right. Hello to everyone on the YouTube stream. Happy to have you here.
Hi, everybody. I'm Ann Isaacs. I'm a first-year graduate student in astrophysics, and I'm going to be presenting on the structure of the universe. So I'm going to share my screen with y'all. I should have thought this through. There we go. So we're going to be talking about the immense heavens, the large-scale structure of the universe. It all started, of course, with the Big Bang, when all of the matter in the universe was made all at once very quickly and then expanded very, very rapidly in a period we call inflation. So this is sort of a brief history of the universe. First, we had the Big Bang at this tiny scale, and then the universe grew rapidly and immensely. Then we have the cosmic microwave background, which I'm going to talk about in a second. And then we had some time when stars were in the process of forming, and then the first stars formed. And then we get to where we are today with the current expanding universe. So the cosmic microwave background is the first light we can see. Before this, essentially, the universe was too dense to see through because everything in the universe, so all of the galaxies and stars and matter we see, was made all at once. So before the universe was a certain size, it was all squeezed in so tight that no light could get through it. So we considered the universe to be opaque before that point. But finally, the universe got big enough that some light could get out, and it is the cosmic microwave background. It's the first light we can see. This was actually discovered on accident by some researchers who couldn't get this annoying hiss out of their telescope, and they went to some other researchers who said, well, that's wonderful. That's exactly what we're looking for. So it's a very fun moment. Now, the overall cosmic microwave background is pretty much, if you look at it on a large scale, if you just say, well, you know, I'm looking between maybe 2 and 3 degrees Kelvin, it looks pretty similar. But if you look a little closer and look at these very tiny differences in temperature, you get something that's not smooth at all. You see these very tiny fluctuations. So like right here, it's very cold. There's not a lot of energy there. Right here, it's very hot. There's a lot going on there. And that's going to come in really handy later when we talk about the large scale structure of the universe. So this is the background. This is the first light we can see. This is sort of the stage onto which the universe forming emerges. So what does the universe look like on a large scale? Well, if we zoom all the way out, we don't actually see a smooth universe. We don't actually see the same amount of stuff everywhere, which is interesting because on some level we might expect that. We might expect galaxies to be relatively evenly distributed. It'd be essentially like, you know, throwing a bunch of sand onto a piece of paper. You'd expect it to be pretty even. But what we actually see are these clumps and voids. We see this sort of filament structure where these bright dots are where there's lots of galaxies, and these dark places are where there's just not much at all. And these actually come from the very early fluctuations, because where there was already, a little bit extra stuff, a little bit more matter than normal, the galaxies were able to start coming together. The stars were able to start forming. And where there wasn't very much stuff, where it was cool, where there wasn't much happening, that was already on its way to becoming a void. So that's really cool, because it means that these very early on, these just kind of tiny random fluctuations when the universe was, about the size of a pea, became the large scale structure we see in a universe that is too big to wrap your head around. So what are these structures? First, clumps. Galaxies tend to clump up together because of gravity. So you're probably familiar with gravity. Massive objects tend to move closer to each other. We call these clumps clusters. So this particular one is called Laniakea, meaning immense heavens, hence the title of this talk. It includes things like the Hydra supercluster, the Centaurus supercluster, the Virgo supercluster, and our local group in blue. So this is just a bunch of galaxies that are all gravitationally being pulled together or interacting with each other. But what's really interesting is that a lot of this is dark matter, actually. Instead of just the light matter we see, a lot of this gravitational interaction is too strong to be explained with just what we see. So that's why we come up with the concept of dark matter. It's called dark for two reasons. The first is because we have no idea what it is. And the second is that it doesn't interact with light. The light matter we see, the normal matter, we see because light bounces off something and then comes to our eyes. So that's how we see things. But dark matter doesn't interact with light, so we can't see it. The only way we can study it is by looking at how it interacts with gravity. So this is hence dark matter, because we can't see it. And if you look at these clumps, at these clusters, you know that there must be dark matter there, and that's part of what's pulling everything together. In fact, we currently estimate that dark matter is up to 25% of the universe, possibly even more, and normal matter only makes up about 4 to 5%. So if we're looking at these big clusters, it's not just the matter we can see, all of these galaxies and stars and hot gas, it's all this dark matter we can't see that's drawing everything together. On the other hand, we have voids. I've included a picture of a void for your edification. I hope that helps. A void is a place where there is not very much happening. There are no galaxies, no stars, no hot gas. There might be a few things floating around, but there's just not much there. And you might think voids are a natural consequence of things being drawn together, because if, something's being drawn over here and something's being drawn over here, the stuff left in the middle, there's not going to be anything left in the middle. And that's fair, but when we actually try to model it, when we try to make a fake universe in the computer that way, it just doesn't work out. We come to the conclusion that there must be something in the voids pushing away. It's not just that gravity is drawing things together, it's that the voids something in the voids is actively pushing things away. And that's what we call dark energy, a mysterious force that seems to push everything apart. Dark energy is called dark energy because we have no idea what it is. It makes up about 70% of the universe as far as we understand it, and it is just pushing everything apart. We also have some other structures. One of them are called the Great Walls. This particular picture is the Sloan Great Wall, because the Sloan Digital Sky Survey discovered it. And so if we're here at this point looking outwards along this cone of sight, we see this sort of big wall of galaxies. And these are sort of strings of galaxies that form the appearance of a wall. And they're these clumps of huge superclusters that come together to make huge structures. So this is basically what we would see if we looked at a filament, because there's these clumps and there's the filaments that connect the clumps. This is a filament. This is a huge clump of stuff that makes up this massive superstructure. So that's pretty cool, because it means that we're looking at incredibly gravitationally dense areas. And we see one beyond Sloan that I don't remember the name of. But again, like, this is a structure we see. There's a few of them, which is quite cool. On the other hand, we see a phenomenon called the fingers of God. So this was pretty astounding to astronomers when they first discovered it, when people first worked out that you could look at the universe, and they they took a bunch of measurements, they plotted it all on this nice circular plot, and they saw what appeared to be lines pointing at us, pointing at the middle, which was a little bit concerning at first, because one of the tenets of physics and astronomy, and generally speaking, is that we're not special. Our solar system, our galaxy, nothing about us is unique or special. It's just, we're just another part of the universe. So it was a little bit concerning when it looked for a moment like the entire universe was pointing at us. And so hence it was called Fingers of God for a brief time. But what actually is going on is that this is an interesting illusion because of how we measure distance. There's a certain relation called the Hubble relation that relates velocity to distance. So the speed of a thing is related to its distance. So what's happening is that in this sort of line, this is actually a cluster of galaxies. And because they're all gravitationally interacting, they're actually kind of rotating around each other. So some of them have a little bump of velocity moving towards us, and some have a little bump of velocity moving away, which complicates all of our measurements and means that what's actually going on is that this is a clump of galaxies, not an extended line. So the universe is not pointing at us, which is very much a relief to the early astronomers. But this is still a very cool illusion, and one you can see in a lot of modern, well, some modern, but a lot of slightly older versions of this before we had a better knowledge of how to compensate for it. So all of this leads us to something called the Lambda Cdm model. So this is a simulation using the Lambda Cdm model, and it looks a lot like the first picture I showed you of the large-scale structure of the universe. We've got clumps and filaments and voids. So Lambda Cdm includes two big things. The first is CDM. CDM stands for cold dark matter. So it's dark matter, it's made of some kind of particle, and we call it cold because it doesn't have a lot of energy on its own. It's not interacting with itself. It's not, if you think of a hot gas or something, it's not doing anything. It's not like putting out any extra energy. It's just kind of sitting there being cold. And it also includes a constant dark energy, which is usually represented by the constant lambda. The Lambda Cdm model is the most successful model of our universe so far. So right now, when we make a fake universe in the computer where we, make a bunch of particles and plop them in the universe and set the right, constraints and ask it to go for a while, we get a result that looks pretty much like the universe we live in. Neat. But that doesn't mean that there's not more to it that we don't know, because we don't actually know exactly how much dark energy we have, exactly how much dark matter we have, and we certainly don't know what either of those things are. So that's pretty cool. Lambda Cdm, successful so far. And as far as we know, what we can do now is really dial into this model and figure out what exactly it means. Another really cool thing we can do, though, is now that we're like, okay, we're pretty sure we know what the universe is made of. We're pretty sure that we got dark energy, we got dark matter, and the dark matter is behaving in a certain way. The next question we can ask is, what is the shape of the universe? Which is kind of a strange question. Because if you think of the universe, you're probably not thinking of it as shaped. You're thinking of it as like in a massive expanse of space, which is very fair. The three possible shapes are closed, open, or flat. And it's pretty hard to explain these in three-dimensional space. So I've got this two-dimensional picture. It's very confusing to think of, but we're gonna just kind of go for it. So first is the closed universe. This is where the universe sort of wraps back in on itself. It doesn't go on forever, maybe, it's closed. With this triangle here, we think of the triangle would end up having larger angles than normal, and yeah, it's sort of a four-dimensional equivalent of a sphere. So we're gonna roll with that for now. The open model is this one here. It's sort of a saddle shape in two-dimensional space. I have no way to picture this in three-dimensional space. You're gonna have to take my word for it that this is possible. The universe is open. In this case, we can see this triangle has smaller angles than normal. And then the last one is the flat model, which is kind of the least interesting, where the universe is just flat. In the two-dimensional space, this is flat, like a table or a piece of paper, whatever you could think of. And that's the most intuitive one. So our measurements right now tell us that we're pretty sure the universe is flat in shape. but it could have a very slight curvature that we can't see. In the same way that when you're standing on Earth, it doesn't look round because you don't have that perspective. We're standing in the universe, so we don't necessarily have the ability to sort of zoom out and see the whole shape. On Earth, you can, leave Earth and take a picture of it and see that it's a sphere, but you can't really leave the universe and take a picture of it to see what shape it is. So our measurements right now say it's flat, but we occupy such a small part of the universe that there is absolutely a possibility that the universe could be a different shape and we just aren't able to observe it fully. Here's a fun one though. One theory, fringe theory, almost certainly not true. Is the observable universe larger than the universe? Probably not, but here's how the theory works. Essentially, we have a closed universe. And what's happening is that we're at one point, and we have these galaxies that are close to us. And very distant galaxies are actually the same galaxies as the very close ones. But the distant galaxy's light has traveled all the way around the universe to get back to us. So the idea is that the galaxies very close to us are actually the evolved versions of very distant galaxies. And so we end up with this weird loop of light. We're actually pretty sure that our universe isn't closed, so this almost certainly isn't true, but it's kind of a fun thing to think about. So we're pretty sure the universe is flat, but now the question is, how is it changing? Because we used to think the universe was steady. Very early on, when people were sitting there being like, I'm sure that there are celestial spheres and the sun rotates around the Earth, everybody sort of considered the universe steady. It wasn't doing anything. They didn't think it was evolving, really. But what we actually see is that the universe is expanding. So the four sort of ideas of what's going on is that there's this universe, the first universe is the sort of in and out. So this universe started with the Big Bang. It's expanding right now, and at some point the expansion is going to stop and it's going to close back in on itself and come together. We'll talk about that sort of scenario in a minute. There's also this one right here where the universe is expanding right now, but at some point it's just going to kind of reach its final size and stop expanding, and it's just going to be done. And at that point it will be steady forevermore. There's also the idea that the universe is essentially coasting, so that it's at its current size now, it's getting bigger, and it's just going to kind of keep coasting and getting bigger at the same speed forever. And then there's the accelerating universe, where the universe is getting bigger and bigger, and it's getting bigger and bigger, faster and faster and faster. And that's what we think is happening. We're pretty sure the universe is we know the universe is expanding. And right now it seems our measurements tell us that it's expanding at a faster and faster rate. And we think this is because of dark energy, which, like I said, pushes things apart. So it makes sense that if we have a lot of dark energy, it's going to push us apart. And the one theory actually is that dark matter is an inherent property of space, so it's self-propagating. As the universe gets bigger, there's more space, and therefore there's more dark energy, and it's pushing out. And yeah, to be clear, the whole universe is getting bigger all at once, all together. It's pretty cool. And so everything is moving away from everything else. The same way if you have a raisin bread and then you cook it, you bake it, sorry, I hope you don't. I've never made raisin bread. Anyways, if you bake the bread, all the raisins get further apart from all the other raisins. That's what's happening in our universe. Everything is growing further apart from everything else, and we're pretty sure it's doing it faster and faster. So what does that mean for the future of our universe? Well, there's a few different possibilities, but for the anxious of you, none of these will happen for billions upon billions of years. But here's what they are: the Big Crunch, the Big Rip, and the Big Freeze. So I mentioned that the Big Bang happened, the universe got expanded very rapidly, and then it slowed down for a little while because there was a lot of gravity and all the stuff was being pulled together, and then it started speeding up again, and we don't necessarily know what's going to happen next. It might decelerate again, it might accelerate again, or it might kind of keep accelerating at the same rate. So let's talk about these one by one. First, the Big Crunch. In this one, dark energy somehow loses its influence. It's not as strong as we thought, or it just runs out. Somehow, the universe collapses back in on itself. Gravity takes over again. Everything in the universe comes back together and crunches down back to a singularity. One theory is actually that the universe sort of pulsates in and out. It crunches down, does a big bang, and expands again, crunches back down, and so on and so forth, which is an interesting theory. We're going to talk about that in a minute. So that's the big crunch. Then we have the big rip. In the big rip, essentially dark energy becomes so powerful that the universe completely tears itself apart. Even atoms can't stay together. So essentially, dark energy will become so powerful that no other force in the universe can keep things together. And everything is just torn apart completely, and it all just falls to pieces. A little bit nerve-wracking. Again, we'll talk about the likelihood in a minute. And then finally, the big freeze. So this is what people refer to as the heat death of the universe. The heat death of the universe doesn't mean that the universe dies in a very hot, energetic way. It just means that there's no more heat left. Basically, the universe continues to expand, but it won't tear itself apart. It'll just kind of keep expanding and getting bigger, and things will grow more and more distant, and eventually all the stars will burn out, and all that's left is a cloud of cold gas floating around forever. So all these probably sound a bit grim. But for what it's worth, again, none of them will happen for billions upon billions of years, and we have plenty of time to enjoy life here on Earth in the meantime. So, what we think we know for now is that the universe is probably not going to do a big crunch. So this plot is, again, like this, the big crunch, this is the big rip, and these two here are probably closer to the big freeze. So these black dots are data, and they pretty successfully don't match the big crunch. So we're pretty sure that this isn't what's going on. And if we track them all the way back, it looks like they're closest to matching the accelerating universe. It looks like what we have here is possibly a big freeze, possibly a big rip. We don't know enough to say for sure yet, but it does seem that our universe, according to this data, is accelerating at an accelerating rate and is headed in the direction of either getting very cold or completely tearing itself apart. So generally, what we're pretty sure we know is that the universe has structure to it. We know that the universe has structure to it. It's not a flat, uniform space of stars and galaxies. It actually, because of very early, just tiny little differences in density, we end up with these clumps of galaxies and voids and all this cool stuff. We think the universe is flat. Not so sure about that one, but we think that's what's going on. And we're pretty sure that the universe is expanding at an accelerating rate. But as for what's happening next, all we can say is that we're pretty sure it's not going to be a big crunch. How about what we don't know? We don't know for sure what shape the universe is. We think we know, but we don't for sure. We don't know what dark matter is. We don't know what dark energy is. We know a little bit more about dark matter than dark energy, but we still don't really know what they are. And there's a lot of ongoing experiments to try to detect dark matter, to learn what it is. And we definitely don't know the fate of the universe. We don't know what's going to happen next. There is part of what makes cosmology such an exciting field is there's so much left to discover and so much left to learn about it. There is infinite wonder in this field. Okay, so the title of this talk was Cosmology and Large-Scale Structure, Why Nothing Really Matters. So what does it mean for us? Well, the universe is unimaginably huge and unimaginably old, and we are a tiny pale blue dot. This is the famous pale blue dot photo of Earth from, I believe, one of the Voyager probes. And this is a zoomed in photo. This is a probe that is not all that far because we can't get all that far, and it still turned around and Earth was just this tiny little dot. So on some level, I guess it doesn't matter very much at all because none of this will happen for billions of years. Most of it happened billions of years ago, and really we're never, well, maybe not never, but the odds of us, getting to another supercluster are, well, it's not going to happen in my lifetime, I can tell you that. So what's the point? The point is that we get to marvel at our incredible universe. We get to look at these incredibly grand structures and learn all this cool stuff about how the universe functions, about all these mysterious forces. We get to learn about the past of our universe, which happened so long ago we can hardly comprehend it. We get to learn about the future of our universe, which is maybe a place we're going to live. So we have the incredible privilege of being here on Earth and getting to look out from our tiny pale blue dot at the incredible majesty of the entire universe. And I think that's pretty cool. Thanks very much for all your attention. I'm actually going to turn you guys over to Darcy now, who's going to show you guys a really cool activity. Thanks very much.
Jump in, because that's not the order we're going in.
Oh shoot, I'm sorry.
I will bring up Darcy so that we can do some question and answer on the talk, followed by the activity. Our first question is from our audience here at the Bell Museum, well, here, virtually here, and it is from Leanne. Leanne says, going back to the fingers of God, can you clarify what you meant by a clump of velocities moving towards us and a clump of velocities moving away from us? Also, thank you for a great presentation. For those of us not studying cosmology or astrophysics, you did a great job with analogies and lay language, which is a comment that I, as Alexander, agree with. That was a great talk. Thank you.
Oh, thank you. So what I mean by this is that in any galaxy, every galaxy is moving apart from every other galaxy. And this is the primary way we measure distance, because the further away from us it is, the faster it's moving. But it also might be, in its own respect, moving a little bit on its own. It might have some what we call peculiar velocity, which is one of my favorite terms in astrophysics. I'm trying to think, sort of like in the same way, if you're on an airplane, you're going at a certain speed, but you can also walk up and down the aisle and give yourself a tiny little boost in speed. So if there's a galaxy that's part of this cluster, it's moving overall at the velocity of the cluster, but it might also be, you know, metaphorically walking up and down the aisle, so just like moving a little bit forward or a little bit back. And that'll affect what velocity we think it's moving at, which means that when we take that individual galaxy's velocity and use that to calculate the distance, we might perceive it as actually being a little closer or a little further than it actually is. I hope that helps. Tell me if it doesn't.
All right, thank you for that answer, Anne. We have one from the Universe at Home YouTube stream. Peter asks, do you know if there is a difference in the redshift expansion rate of the universe along the galactic filaments versus along voids, for example?
I don't believe so. I believe galactic expansion, my understanding is that galactic expansion should very much be universal. There's no reason to believe that galactic universal expansion is universal. The voids may have a higher concentration of dark energy, but nobody has successfully measured a difference in expansion, I believe, outside of like a couple of local disturbances.
And I would add that those local disturbances are areas in which for example, in a galaxy cluster, those galaxies, their motion is dominated by the gravitational attraction that they have to other galaxies. It's not that they're not affected by the expansion of the universe. It's just that other things are dominating the physics of that situation. We have a very relevant question from Adrienne here from the Bell Museum audience. Since the universe is expanding, does that mean that all objects within the universe are also expanding, like stars, planets, people, atoms, etc.? Oh no, the question disappeared on me. Let me try to find it. To use your analogy, are both the bread and the raisins expanding, or just the bread?
Just the bread is expanding. Only the raisins are staying the same size. This is part of why the big rip might happen, because the space is expanding, but the stars and galaxies themselves are not. So the space between them could become the problem, actually. There is a theory that eventually the expansion of dark energy will be so great that we can't see other galaxies because the speed of light can't overcome it. So yeah, the objects themselves aren't expanding, which is how we're able to measure it.
Sorry, just checking that I'm unmuted. Another question from the stream by username Peace2051. Is there any theory or mathematical suggestion that dark matter has phases similar to normal matter? By phases, I take it they mean water, ice.
Solid gas? Not currently. There is so little we know about dark matter that it's hard to compare it to normal matter. Maybe, generally speaking, people assume that dark matter is made of one kind of particle, and so people have been like, well, what if there's multiple kinds of particles? Generally, I believe we think of it as a gas, but I don't believe there's any evidence for phases. If somebody else wants to jump in on that one, that's completely fair.
I have seen some very theoretical treatments of this sort of thing. As astronomers, we usually think about it in terms of, like Anne said, single particles that are fairly diffuse. But if you get far enough into theoretical physics, you can find folks that have theorized phases of dark matter that function just like phases of normal matter. We just don't really have any evidence for or against that sort of behavior yet, because like Anne said, we call it dark matter because we don't know what it is. We've got another one from the Bell Museum audience here. How can we say that the universe is flat when it seems to be so immense in all directions from any point on Earth looking up at the night sky? That is from Bob.
Well, Bob, you've successfully pinned down why we're not sure the universe is flat, because we just can't see that far. Our measurements are very bright, what we call transients usually, which are very bright temporary events. And they're powerful enough that we can see them from very great distances, which allows us to make certain measurements about the flatness or otherwise of the universe. That said, there's only so far we can see. So the conclusion we come to is that the universe seems to be flat. It's not so dramatically curved that we can see it in the scales that we are capable of measuring. But we don't know for sure that the universe is flat. It absolutely could be slightly, we don't think it's closed because of various measurements, but it absolutely could be very slightly curved one way or the other.
Another one from the YouTube stream. Is dark matter uniformly distributed throughout the universe, or are there pockets that are more or less dense?
It is definitely put in pockets, because dark matter is affected by gravity, so it tries to pull itself together in the same way that normal matter does. So, for example, the dark matter in the Milky Way is, there's a lot of it. It's less dominant at the center, but it's not, there's a halo of dark matter around the Milky Way. And then if you went out into a void, there wouldn't be very much dark matter there at all. Or again, there's dark matter in superclusters that's part of the supercluster, but would be found in much smaller densities outside the supercluster. So yeah, in the same way that normal matter likes to cluster together, dark matter absolutely likes to cluster together.
Something that's also, I think, interesting, our galaxy is mostly like regular matter, but they have discovered a galaxy, it's called Dragonfly 44, which also just sounds super cool. That is, excuse me, Kat. She's making an appearance, I guess. It is 99.9% dark matter. So most of that galaxy is dark matter, which is very different from our own galaxy.
Have another question here from the Bell Museum audience, which I think is a rather fun one. Would you say that the universe obeys Newtonian laws? Which is a surprisingly deeper question than it may appear on the surface.
Yeah, you're getting into the attempted unification of quantum theory with, special relativity. On some level, Newton's laws work in certain limits, because you have a lot of things in the universe move very fast and have to have relativity applied to them. And a lot of the things in the universe are very small and have to have quantum mechanics applied to them. But on some level, we can model a lot of behaviors of, for example, galaxies with relatively simple Newtonian mechanics. I learned about what we like hydrostatic equilibrium in stars, which is to say that stars, they have gravity pulling in, pressure pushing out, and those things keep them at an equilibrium. I learned about that through pretty basic Newtonian mechanics. The forces have to balance out so the acceleration is zero. So yeah, complicated question. On some level, some things do to a pretty good approximation, but we certainly can't always say that all things obey Newtonian mechanics. Goodness, I hope that's a good response.
I thought it was. We have another one from the YouTube stream from Ron. who thanks us for the talk. You mentioned that there are 3 potential shapes to the universe. His question is then, what happens if something were to travel at a normal to that surface, such as up for the flat universe?
Oh, geez. This is part of why they're hard to conceptualize. If something just went up forever in the flat universe, it would just kind of go up forever, or at least until it reached the edge of the universe, if such a thing exists. If it were the closed universe, no matter which direction you go, you'll eventually end up back at the place you started at. I especially struggle with conceptualizing the open universe, but I believe that you would end up further away than you might expect in the flat universe if you just sort of picked one direction and went. You'd be like, wait a minute, I'm further away than I thought I should be. And again, you would not get back to where you started unless you turned around and went back. Yeah, the shapes of the universe are difficult to think about.
We have another question from the Bell Museum audience, and I think that pretty soon here we're going to switch over to Darcy, and they will lead us through an activity related to today's talk. But the last question for now from the audience is going to be, is there any way, and this is from John, is there any way that black holes will consume the universe into one big black hole?
I mean, I suppose nothing's impossible. It seems unlikely because black holes don't actually draw in matter. If matter gets inside of their critical radius, they'll eat it up, but they don't actively draw in matter. That said, many black holes are actively eating and, taking in matter, but they also do radiate away very gently. You may have heard of Hawking radiation. Black holes very slightly release some of their energy. So I don't think it's likely that black holes will eat everything and make the universe into one big black hole, but I guess it's possible. And one fun fact is that some people believe we already live inside of a black hole, and we're just like a universe that exists inside of a black hole. So that's a fun thing to think about in your free time.
All right, well, thank you very much for all of your incredibly elucidating answers, Anne. We're going to hand things off to Darcy here, and they will lead us through an activity there.
Yeah, so I've got an activity based on our look at the structure of the universe. I'll need to share my screen real quick. So this is the CMB, the cosmic microwave background, where we saw that some things are hotter, some things are a little colder. This is the structure of the universe, how things clump together. Keep in mind kind of how this looks. And then we see that kind of saying, hey, stop drinking milk. Sorry, my cat's a horrible cat. The stars will clump together in areas as well. This kind of comparison between a brain cell and the universe is something that I think is pretty common on the internet. A lot of people may have seen this picture. So I thought I'd make a game and we can see if we can figure out what these different pictures are that I think look kind of like that clump and that shape of the universe. So this is the first picture. I'll give a little bit of time. We'll see what people have guesses. You can send them in on the chat function in the YouTube live stream. And I suppose you could send it on the Q&A as well if you're doing this through Zoom. One person here said city lights. And that is correct. Let's see if I can get back to the right page. Yeah, so this is city lights. This is light pollution from a light pollution map of Europe. I think light pollution is something that we've talked a lot about. So I think light pollution maps look very pretty, but unfortunately they light pollution's not super great for astronomy. Here's this next one. Someone said roads, collagens, steel wool, cobwebs. I'm having a lot of trouble having so many things open at once. I think I've confused my computer. So if Alexander could read the guesses.
Absolutely, I'd be happy to.
Great, thank you. This is just very zoomed in cobweb, but I think it's neat that something that most of us dislike looks so much like our universe.
All right, we have city lights again. We have brain links, plasma, lava. It's a fun one.
So I guess this one is a bit of a trick question. This was, again, just what our universe looks like, the kind of clumps and filaments of our universe.
Ooh. We've got bread. A couple guesses for bread. 3 guesses for bread. A sponge, insulation. That's a good guess. Cotton candy, gum. Definitely bread.
Yeah, this is a picture of bread that I turned purple. Because the last picture of the structure of the universe always makes me think of the nice little bubbles you get in bread. So I don't know, maybe our universe is delicious.
We've got tree, branches, rug, roots, vines, a lot of organic moss, a lot of organic materials, dried seaweed, dried moss, cellulose, got some disagreement, folks saying it's definitely not moss, hair, a loofah, lichen. Oh, they're coming in now. End of season weeds. That's a good one.
Yeah, so this is a picture of a root system, which I think roots are super cool. And I think neat to compare the differences, the similarities between roots and our universe.
So I think this one's an album cover. We've got city lights again. A couple people saying that. Seems to be the consensus for the moment.
Yeah, this one is very similar to the city lights. This is actually population density, which generally where there are more people, there are more lights. But there are definitely areas where a lot of people can live and you don't have nearly as much light pollution. So this is the last one.
All right, make them count. We've got our guesses coming in here. Squash, mold, lichen, corn or pineapple. I mean, they're coming in. Bacteria in a Petri dish. Wendy says mold. Tara says fried cheese. Yeast. A lot of food-based ones here.
Yeah, I definitely really like the fried cheese. That's very Midwestern. This is slime mold. Which is, I think, particularly interesting because scientists have noticed the similarities between slime mold and the universe structure, and have actually used it to kind of map our universe. Don't drink that. Sorry, my cat is awful. So they actually used that. They published this a little earlier this year. Don't eat that either. They published earlier this year this article about using slime mold and an algorithm based on that to work out between, there are no bad cats, she will give you a run for your money, to kind of work out the kind of gray area between the Big Bang and kind of where we are now with different galaxies and things forming. So I think that's a pretty interesting article. I'm going to stop screen sharing, and I'm also going to put in the chat a link to that, so that if anyone would like to read that a little more, they can look into that.
As you're doing that, we have a very important question coming up from the Bell Museum audience here, which is, what is your cat's name?
Her name is Andromeda, after the galaxy.
Nice. Looks like we do have some additional time here. So if there are any other burning questions that you have about anything that we talked about or general space things, either here or coming from the YouTube stream, we are happy to help out, unless Sally has something else that she would like us to do. She's running the show. We do have a question that I will use to plug our YouTube channel. So Nathan asked what our YouTube channel is called. It is called Universe at Home. We usually type it out with an @ symbol to be all, cool and whatnot, but the YouTube channel is youtube.com/c/universe@home, entirely typed out. At spelled AT instead of the symbol. I see that we've got a couple more coming in here. This is just a fun one from Bob. What is the chance of multiverses?
Ooh, that's a big one too. Personally, I think it's a cool possibility. There's the idea that the Big Bang cannot be a unique event is certainly a valid idea of saying, like, well, there must have been a bunch of other if there was one Big Bang, surely there are others. Gosh, I think the idea of parallel universes as we think of them in sci-fi is probably not very likely, but the idea of there being other universes is certainly not a possibility I would rule out. The likelihood that we can ever get to one, of course, is a bit slim, I would say. Do you guys want to weigh in on this one? Because that feels almost philosophical to me.
Darcy, why don't you go ahead?
I'm not sure. I think a lot of people think of universes or different universes in terms of what we can see is our universe, is our bubble around us of the cosmic microwave background. But if someone somewhere else is looking from somewhere else, they'll get that bubble around them. So they would have their own cosmic microwave background and essentially their own universe. So I think in that sense, there are probably a lot of universes, in the sense that, like, kind of like Anne said, like, there's an evil me who's, I don't know, like, evilly studying here or something. Probably not. But a lot of very well-known physicists, I believe Stephen Hawking did mention that he thinks it's likely there are different universes where they're similar to ours, but different in some way.
I think I mostly share Darcy's perspective. And I think where I would diverge from what they said was that, like, there may very well be all of these parallel universes, but I think I take a bit of a practical perspective on it, that as far as we can tell, we don't have any way to access them. So functionally for us, do they exist? If you can't see it and you can't go there, it unfortunately ends up lying more in the realm of the imagination until, if or until we manage to figure out a way to access these, hypothetical other dimensions. We have one more from the YouTube chat. Are there any theories as to the source of the energy to power the acceleration of the expansion of the universe? Which is really the million-dollar question, isn't it?
Yeah, I mean, we say it's dark. We say we believe it's dark energy, but what dark energy is anybody's guess. It might be a form of, it might be a force like gravity. It might be an inherent property of space, that space just likes to expand, and as space expands, there's more space to expand. Those are a couple I've heard. We know it's more powerful than the gravitational force pulling things back together, but not much more than that, as far as I know.
All right, I'll try to find a question from the audience here. Mary Lee says, couldn't that be said of all theoretical physics is existing in the realm of the imagination? Well, you're probably going to tick off a lot of theoretical physicists.
The theory can match up to an experiment, hopefully.
Yep. The standby that we oftentimes go by, and by we, I mean those of us who work in primarily observational or experimental fields, that give me an observable, give me something that your theory predicts that I could actually design an experiment or point a telescope at the sky to figure out and see whether it's true or not. Otherwise, if your theory is unverifiable, what am I supposed to do with this? We have a fun comment from the YouTube chat saying that they are at the star party right now. They say hi. That's Liam. Hello. Ooh, I'm going to take this one because it's my favorite topic. John asks, how will gravitational waves be used to measure the expansion of the universe? This is a thing. I don't specifically study, these are called standard sirens, but I do study gravitational waves, and I find them really cool. So the idea, and I just attended a talk about this the other day, but specifically binary neutron star mergers have both a flash of light and a burst of gravitational waves that go out through the universe. And the gravitational waves can be used to measure the distance to that galaxy, or rather the distance to the binary neutron star merger and whatever galaxy it resides in pretty well. What they're bad at, however, is measuring what we call the redshift of that galaxy. But if you can also observe the flash of light that comes from this neutron star merger, then you have light, which is a very good measure of redshift because it quite literally is how much the light is shifted into the red part of the spectrum. You have both a redshift and a distance, and you can do that over hundreds of events and in various different places in the sky, and figure out basically how fast the universe is accelerating away from us at different points at different distances, and try to see, in astronomy, the farther out you go in distance, the farther back you're going in time, so you can see how the expansion of the universe has changed over time. And I think we have time for only one or two more questions. So let's grab one from the YouTube chat. Oh, that's interesting. So Ron asks, since light really uses no time to travel, is it possible that our estimate of the age of the universe is based on our local reference frame and is therefore inaccurate, that we don't really know how old it is. Do you have an answer for this, Anne?
I mean, I don't think so because of the inherent fact that light must travel at the same speed in all reference frames.
So I think the crux of it, right? A photon is moving at the speed of light, so it doesn't really experience time. But we do experience time, and we can see that photon moving. And the explanation for that gets into some horrific relativity that we don't have time for. But yeah, we know that in our reference frame that the light will move at the speed of light as it's traveling through the universe. And as far as we can tell, physics more or less, well, physics should work the same in every reference frame. There are some caveats to that with relativity, but it overall works. So if you observe something to be true in one reference frame, assuming you're doing it correctly and you know everything that's happening, it should be true regardless of that reference frame. So we think that we're right. As far as we can tell, what we're doing works.
Yeah, and as far as we know, things about our own velocity and things like that.
So I think we'll end with this question from the Bell Museum audience that Phil asked, because I think that's a really interesting question that really wraps all of this up. He asks, is an implication of dark energy that by pushing it apart, eventually it would be moving things apart so quickly that they are moving faster than the speed of light, which, as we know, is physically impossible for an object to move faster than the speed of light.
Yeah, that's absolutely a possibility. It's part of what we worry about with what we think about with the Big Rip. It is a theory that eventually at some point the expansion of the universe will be so great that we can't see any other stars, eventually can't even see our own star, and so on and so forth, because no object would be moving faster than light. Space itself would be expanding faster than light, which is theoretically possible. So yeah, that's absolutely a pretty wild possibility to think about. We don't know if it'll happen, but it is certainly not impossible. There's very little we can rule out at this point.
A very cool aspect of this is that we do actually observe a certain way of looking at this phenomenon in our current universe. Because if you look one way and you look the other very far back in time or very far away, those two galaxies are moving away from us, each individually fast enough that from our perspective, they appear to be moving away from each other at more than the speed of light, which shouldn't be possible. But Anne really got to the crux of it. It's not that the objects themselves are moving as dark energy expands the universe. It's that the space in between the objects is growing larger. In their own individual bits of space-time, they are not actually moving faster than the speed of light. It's just that the combined space between them is getting larger at a rate that makes them appear to be moving away from each other faster than the speed of light, which is a very odd distinction, but it's important to make the physics work out. And with that, I believe that we are out of time. So a big thank you to Anne and Darcy for all the work that they did to put this night together. A round of applause. I think I'm one of the few people who can actually do that. But
well, and thanks to Alexander for organizing all of the tech stuff and, you know, pulling a lot of this together. Definitely pulling his weight.
Of course. And thank you so much to the Bell Museum Statewide Star Party for hosting us. It's been a pleasure.
We're so happy to have you. You all did a great job inspiring our audiences to really start thinking deeply and philosophically about the universe. It was really exciting also to have your YouTube channel join us here for the Statewide Star Party, to have two groups at once. So thank you once again, Darcy and Anne and Alexander.